We're going to grade the exams tonight, and as usual, you'll get your scores late tonight, and then they'll be returned in class on Tuesday, but if you want to see your exam before then, just come by the office on Friday from 3 to 6, and you can get your exam. All right. Now, we're starting the last section we're going to do. It's on hypothesis testing, on significance tests. And I think you're going to like it. I mean, students usually do. This is usually their favorite part of the course because it ties everything together from the very first day of class. Remember the first day of class when I asked you to imagine the ideal experiment? And we decided that and we were going to test this new drug that was designed to make you smarter at learning statistics. So we figured out that the best way to do that would be to do what? To randomly assign half of you to the pill, to the real drug, and then randomly assign half of you to the placebo. So you wouldn't know what you were taking, and then it would be double blind. I'd have no idea which ones you were taking. So then at the end, let's imagine now it's I'm doing the grades. It's the last day of class, okay? And finally that blind is broken and I get to see who was in which group. And I want to find out, okay, did the drug work? So what do? I take the average score of everybody in both groups, right, and compare them, right? Isn't that the best way to do it? Yeah, so that's what I do. That's what I do. Now let's say I see some difference of maybe the drug group got a score, average score of what, 90, let's say? And let's say the other group got an average score of, maybe 86.9 or something. That's only like just about a 3.1 point difference. Is that big enough that you can say the drug worked? It's a huge difference in terms of your grade. One would be a straight B and the other would be an A-. It's a big difference to you guys, but it's just a few points. Can you say the drug worked or not? If the difference was a 70, between a 90 and a 70, of course you would say the drug worked, right? Absolutely, but what if it's just the difference between 89 and 90? The idea is, imagine this. What if the drug really didn't work? If it was a complete and utter dud? The two drugs were they're just both sugar pills. Now, would you expect, I randomly assign you to each condition, half to one, half to the other, would you expect there to be exactly the same averages between the two groups or not? No. Why not? It's a dud. It's like basically neither group took anything basically. They're both placebos. Pretend it didn't work. Then it would be like, would the average between the two groups be exactly the same or not? What do you think?
There's differences in the group too.
Yeah, there's differences between the two groups just because the luck of the draw. You're not going to get exactly the same average. You're different groups of people. Right? You wouldn't get exactly the same average, would you? I mean, if I took it out to many decimal places, do you really think imagine this. Imagine all your scores, all 1,100 people's scores in a box with tickets on it, and on each ticket is written your final score for the semester. Oh. Each ticket is written your final score for the semester. Now, I thoroughly mix them, and then I take out half the tickets and leave the other half in the box. And I take the average, because neither group got the drug, right? So they're both placebos. So do you think the average of the half that I drew out is going to be exactly the same as the other average that I left there? No. I mean, I could have more just top scores in one group than the other. I'm going to have some difference, right? So the question is, how do you know? How do you know? At what point do you know that a difference that you see between what you observe this difference and what you'd expect if it was just due to luck, how do you know? How big does that difference have to get before you can say, hey, it was due to luck? The drug didn't work. At what point?
That's what you're about to tell us.
That's what this is about. Yeah, that's what this is about. So we can finally answer this question. Okay, so it's a statistical, what these hypothesis tests are statistical tests to determine whether a difference you see, a difference you observe is real, meaning it's due to some particular cause, or if it's just due to chance. All right, now what do we do? So we set up this null, maybe it's best to work out a real example, okay, that actually happened to me, and you'll see what all these mean in terms of a real example. Okay, let's do that, because I can see that you guys are tired. Me too, after the exam last night. So, I came up with this example because I used to teach these giant classes in the math department where they had discussion sections, like I wish we had in Stat 100. And I used to have a big lecture and a little section of about 30 people. And one time when I was doing this, I think I was teaching calculus at the time, I had this early morning section and it was led by this really great TA that I thought was going to do better on the exam I gave, the first exam I gave, than the other sections. I just had this feeling that this group's going to do, first of all, I thought people who sign up for a really early morning class are probably, you know, people who are prepared, a different type of person, and also this TA was great. So what did I do? When I actually got the scores, there was some difference, but it wasn't big enough that it was obvious to me. It wasn't like, oh my goodness, a difference between 70 and 90 that we don't need statistics for. It was just some difference. Is that difference? We don't have a good intuitive feel for statistics. We just don't. Our brains aren't hardwired that way. So I had to do a statistical check, and this is a real example. So a large lecture had 1,000 students. On a midterm exam, the class average, well, it wasn't that low. I made up these numbers to make things come out better. The class average was 70 with a standard deviation of 12. It suggested that the early morning section has more serious students and would therefore have higher scores. And this section had 36 students, and their average was 75. So just looking at that, between 70 and 75, can you tell that was just so unlikely to be due to chance? Can you? I mean, is each section going to have exactly the same average? No. Okay. So the question is whether this 5-point difference, they did do better, is real. I mean, it's because they're really better students, or whether, I mean, there's something different about that group, or whether it's just simply due to chance variation. Then the next exam they might do worse. It's just due to chance. Okay, so suppose it is, so this is an argument by contradiction. You assume that it was just due to the luck of the draw. That these students, there's no particular reason for this. It's just chance variation. They're not going to always get exactly the same scores, all the sections. And you assume that, and then once you do that, you say, well, if it was just due to chance, how likely is it? You figure out the chance. You say, how many standard errors is it away from what we would expect? How far out on the curve is it? How unusual is it? And you can figure out the chance that you'd get such an extreme difference as 5 points just by the luck of the draw. And if that's called the p-value, and if that chance is really tiny, way beyond a reasonable doubt, then you reject that null and you say, hey, there is something different going on here. It's not just due to the luck of the draw. It's very much like our legal system. We assume innocence. We assume that the person on trial is innocent, don't we? Right? And then we accumulate evidence. If he really was innocent, how likely would he be to be right at that scene of the crime with blood on him, let's say? Well, you say, well, maybe he just leaned down, saw a victim there, reached down to see if he was okay, and that's why he has the victim's blood on him. That's some doubt. And then you say, oh, wait a minute, he had a motive. he was stealing from that victim and he has all the money in his pockets. Well, then it brings you further out. If he was innocent, would he really have all that money on him? And he said, well, he was just about to run to the police and he needed money to get a cab to go there or something. I don't know. He made up some story. And then he said, well, wait a minute, why do you also have the weapon that killed that person? And then it's way beyond a reasonable doubt. And you reject his innocence. So we're sort of doing the same thing here. We're assuming that it's just due to chance, and then we're saying, how likely is it that we'd get such a difference as 5 points if it was due to chance? How often does that happen when there's really no difference? Okay, so that's the idea. Now, so we have to set up what's called the null hypothesis, which is like the dull hypothesis. Think of it that. The person's just, nothing's going on here but chance variation. Okay? And an alternative hypothesis. And the null hypothesis is just that it's just due to the luck of the draw. There's no particular reason for it. And the alternative is always, this is there's way too much evidence against that. It's too large to be explained by chance. It's not just an innocent chance happening. Something else is going on here. Okay? And so, what do? So, we set up, if we say it's due to chance, we actually define what we mean by that. We translate the situation into a box model. So let's do that. And let's imagine that we choose 36 tickets at random from a box that contains 1,000 tickets. Why? We have 1,000 tickets in here, and on each one is going to be written an exam score for each student in the class. There were 1,000 students in the lecture. So we'll write that down. On each is written an exam score. Okay, we got that. Now, let's zoom in a little bit. All right, and what's the average of the whole class? Do we have that information? Hello?
70.
Thank you. 70. And do we have the standard deviation of the whole class here? Was that given to us? 12. Yeah, 12, good. Okay, so now we imagine if it was just due to chance, just imagine randomly picking how many tickets out of this box? One for each person in the section, right? We're just going to randomly draw 36 tickets. N is equal to 36, and they're randomly drawn without replacement because, each is a separate student in the 36, in that small early morning section. Okay. So now, what do we observe? Here's the language we're going to be using. We're going to have an observed average and an expected average. So our observed average, what we observe in our sample, called our observed average, is what? Out of the 36 students, what was their average? 75. And what do you think the expected average is? What would you expect if you drew tickets out of here? What do you expect? To get an average of what? 30. What else would you expect? Okay. 70. Did I say 30? That's because I thought you said 30, and I was just expecting you to get the right answer. What did you say?
I said 70.
Oh, speak up more clearly.
All right.
No, really, I thought, he said, he gives me my answers here. Okay, so 30? What'd you all think when I said that?
Yep.
All right, 70. All right, so then what we're going to do is going to compute a z-score. Because we know, why can we do that? Because we know that the probability distribution, the sampling distribution for the average, if we took 36 tickets out of here and computed their average over and over and over again, what would you get? You would get some kind of, you'd get a normal curve, a normal distribution. If you took 36 over and over and over again, and all their averages would follow the normal distribution, with right in the middle would be 70. And we want to know how weird 75 is. Is it way, way, way out here, or is it right here? Where is it? We don't know that until we change this to a z-score. Then it would be 0. Here's our 70, and we want to know just where 75 is. We know it's 5 points away. Some people, where do you think it is? That's what we're trying to figure out. If it's way beyond a reasonable doubt, way out here, and it's just a tiny little chance of happening, we're going to reject the null. If it was 90, we'd know it was way out here, but with 70 and 75, have you heard anything I just said? Because my mic was falling off. Did you hear anything? Raise your hand if you heard anything. Oh, good, because I think what I said was good. I mean, it was important. All right, so we're trying to figure out where that 75 is on here. Okay, you want to guess? How far do you think we have to go out? Here, tell me when to stop. Say stop. Okay, so you think it's right there, 75. Not big a difference, it's only 5 points. So you think the standard error is more like 10, you think, or something. We don't know until we figure that out. Let's figure it out together. Okay, so if it was right here, we'd say, oh, just a chance occurrence. Let's try this now. All right, so we do the observed minus the expected value. All right, this is our z test, our z-score. Okay, and we say z is going to be equal to our observed average minus our expected average. Right here is the difference we see. We observe 75, we expect 70 from that box, so we know it's 5. That's what we know. But we want to figure out whether 5 is here, or here, or here, or here. We don't know that until we know what the z-score is. So we've got to get a z-score. We have to know how many standard errors that is. What's the typical variation you'd get if you did this over and over and over again, drew out 36 tickets each time and computed their average? And that is going to be the standard error for the average. How much does the average vary when you do this? How much does it vary? We'd expect to get 70, but how far away from that do we usually get? Okay, so how do we get this? Do you remember? You did this on the exam last night. Do you remember how to get the standard error for the average? Yeah? Right, it's SD divided by the square root of n, the standard deviation divided by the square root of n. Everybody agree? All right, so let's just compute that. All right. So let's do it over here. So we're going to have SD over the square root of n. All right, so what is that? SD. Do we have it? It's SD. Oh, we even have it here. It's 12, right? Yeah, I don't have any room. It's 12, this I'll just put it down here. It's equal to what? 12 divided by the square root of 36. 12 divided by 6. So that is equal to 2. 12 divided by the square root, 12 divided by 6. Everybody agree that's 2? Yeah? So I'll put 2 right here. 12 divided by 6 is 2. All right. Now, look at this. We get a z-score. And what is our z-score? 5 divided by 2, so it's what? 2.5. Now, that's our z-score. So our next step is to use the normal curve to figure out our p-value. So now, we're just saying, now we realize that 75 is not there. Where's 2.5 on here? Way out, okay? That's what we're doing. We're gonna have to move this 75 way, way, way out. In fact, it's even further than that. Let's look up 2.5 in the back of the book. Between 2 and negative 2, between 2 and negative 2 is 95%. This is probably really, really big. So let's see. Let's look up 2.5 and see what that area is in the middle. And we get 98.76. So it turns out, let's draw this. So let's draw a curve here. There's our normal curve. And right in the middle is a z-score is 0. In terms of exam scores, it was what here? 70. So that's what we've got. And then we said 75 is way, way out here at 2.5. That's where 75 is, way out there. And now we want to figure out the chance of getting this weird a value, 5-point difference, or even more extreme than that. So I'm going to highlight it. It's just a little speck of a chance. Like right here, that's it. Just that little speck of a chance right there. Okay, so between 2.5 and negative 2.5, we know is 98.76, right? So this tiny little thing, this is the chance of getting a 75 or larger. Not at all what we thought. We thought the chance was around there, this huge chance, that it was just, an everyday occurrence. It's this tiny little chance way out here. And that tiny little chance is just 100 minus 98.76 over 2. So it's less than 1%. Less than 1%. So this right here is equal to 0.62%, less than 1%. And that's called our p-value. Have you ever heard of a p-value? I mean, in all the, probably if you've looked at research papers, they always give this p-value, right? And what that is the chance you'd see this extreme difference, or even more extreme, just due to the luck of the draw. Well, this is way beyond a reasonable doubt. If you were sitting on a jury, you'd probably say, whoa, this is just so unusual, and convict the person. Okay? So small values of p are evidence against the null-dull hypothesis that it's just due to the luck of the draw, just innocent luck of the draw. They indicate something else is going on besides chance. So we reject the null when p is really small. Now we can't say, so we say we reject the null. Okay, let's just write that. We'll reject the null. And usually, the conventional number that people use as a cutoff point is 5%. So that's usually what happens if it's less than 5%. This is way less than 5%. And if it's less than 1%, people say, reject the null and say that it's highly statistically significant. That it is a statistically significant difference if it's less than 1%. Everybody would agree to reject the null. So we'll reject the null because p is less than 5%, although that's kind of an arbitrary cutoff point. P, in fact, p is less than 1%, so the language that most people use for that would be that the result is highly statistically significant. So it's a highly this is what I'm just going by these conventions, highly statistically significant difference. This 5-point difference that we thought wasn't much of anything. So this is a big wake-up call to all of us, I think you already knew it already, that we can figure out lots of stuff by common sense, right? But if it's something that you need statistics for, it's extremely hard for us to do a lot of this by common sense. We just don't have a good feel for it intuitively. Okay, so Oh, this is what I want to tell you. So, okay, so we rejected that, null, but now, can we say that, oh, it's the early morning students are more serious? No, we're not sure about that. We know it's due to some cause, but we don't know what. It could be the TA is a better TA. It could be, I don't know, he had a copy of the exam ahead of time and actually told him what was going to be on it. It could be a lot of different things, but we don't think it's due to chance. That's all we're saying. Okay? So, any questions on that? Let's go to the next one. Oh, by the way, that other exam, example we just did, about 5 years ago or 6 years ago, I think it was, when I was teaching Stat 100, after I did that example, a student came up to me after class and said, hey, could I do a statistically significance test on a situation I'm in right now? He said, I'm in one section, and my roommates are in another section of a very large course. There were just basically two giant sections. And our exam averages are 1 point lower than theirs for the past 3 exams. So each exam, or maybe 4 exams that he had, each one was 1 point lower than his roommates. And it's making a difference for him because he's getting a B and his roommates are getting an A. So, and a lot of people had complained already. They felt like one of the tests was harder. And the main instructor for both of the sections said, it's just due to 1 point. Come on, scores vary, it's just 1 point. You can't, it's just due to luck. What are you talking about? So maybe it was more than 1 point. It was 1.5. I can't remember exactly. But anyway, I think it was just 1 point actually. Is that right? Because it happened 4 times. Okay, so I said, yeah, we could do a significance test. So I explained a little more to him than what we just did. And he went to his professor and he said, you say it's due to just chance variation. What is the chance of that happening 4 times in a row like that with this many students? And the professor said, well, what do you mean? He says, well, did you calculate the chance? And she didn't even know it was possible to do that, let alone doing it. She didn't know it was possible. So he said, well, just estimate then. So she said, oh, it happened all the time, She said something like 50% of the time we'd get something, or not 50%, because that would be really dumb. She said, because even if it's like flipping 4 heads in a row, even if it's just 50% of the time. But so she said, all the time, like 30%, 40%, something like that. And he said, well, actually, I've calculated it, and the chance is extremely low. It was less than 1%. And she just looked dumbfounded, and he said, I'll leave you the work. So he just left the work, and he went home. She didn't say anything then. And then shortly afterwards, everybody in the class got an email, this is a true story, saying, we've adjusted your average scores in the lower class 1 point, so that we've given you all a point, so it was good. So it's kind of a cool story. So what I'm telling you is, it's not so important that you know how to do the calculations as it's important to know when you can use a statistical answer and when you can't. She didn't even know it was possible to answer that question. So mainly what I want you to get out of Stat 100 is figuring out when you can use statistics to find something out and when it's not going to help you that much. Okay, so let's look at this example. So an experiment on ESP was done at UC Davis to determine whether people thought to be clairvoyant really had ESP. A machine called Aquarius used a random number generator to pick 1 of 4 targets, and the subjects tried to guess which target the machine chose. Okay, so there were 15 of these people claiming to have ESP, and each of them made 500 guesses. So 15 times 500 is 7,500 guesses. And out of these, what did they get? They got 2,006 were right. So we're comparing This is what we observe. And what do we expect? How would we figure out what we expect? 2006 we're right. What would we expect? Let's think about it. All right. So the null hypothesis is what? What's the null hypothesis? That it was just due to the luck of the draw. These people were not clairvoyant. So the null hypothesis is that the difference we see between 2006 and what would we expect? If there are 4 targets and people are just guessing, right? How many would you expect them to get right? 1 out of 4, correct? Correct? 1 out of 4. And how many guesses did they make? 7,500. So if the subjects had no ASP, they'd be right 1/4 of the time. That would be 1,875. So we're looking at the difference between these two numbers. And what is that? That's the difference. That's the observed minus the expected. And could that be explained by the luck of the draw? So we'll set up a box model, and the null hypothesis is always based on some probability model. That you say it's due to chance, so you have to say, what do you mean by that? You can't just say, oh, it's due to chance like that professor did, and not think about, I mean, you can say that, but it's not going to help you with this statistical check. You have to say, what do I mean by that? Does this translate into a probability model or not? You know, if the teacher had said, if the professor had said, well, the exams are somewhat different. You know, one person writes one exam, somebody else, so they are somewhat different. Or if she said something else along those lines, well, then we wouldn't need to use a probability model. She would have a reason for it. But if she's saying it's just due to chance, well, then you have to translate it into some model. Okay, so our model is they're just guess. The null hypothesis, the dull hypothesis is that they're just randomly guessing. 1 out of the 4 targets is right. And they're guessing how many times. So this is called the null box. Okay? And the null hypothesis is that this difference right here between observed and expected is very small. And just due to what? To the luck of the draw. Yeah, a chance. See, it's just due to the luck of the draw. So you have to set up some draw. That's what it means. You have to imagine what it translates into. All right. Now, and the alternative hypothesis is what? Well, there's lots of alternative. We don't have a particular alternative hypothesis in many cases. Sometimes you do. In this, well, I guess you could say they have ESP, but no, it's just the alternative hypothesis is just that there's some particular reason for it. We're not sure what it is. Maybe they cheated, faked the results, who knows. So the difference is too big to be explained by chance variation. They're not just guessing. Something else is going on. It might be ESP. We'd have to do another experiment. It's too big to be due to chance. Okay? They can't just be guessing. They're not just guessing. Something else is going on. All right. So that's the idea. And now what's n in this case? Well, how many guesses did they make? This is n right here. So n is equal to, and it's a guessing game, so the draws are made with or without replacement. Each time they guess, the chances stay the same. Okay, so it's with replacement. There's only 4 tickets in there. And just our observed, what is this? Is this an average, a sum, or what are we doing? We're counting up the correct answers. So our observed sum is, what did we observe? They got more right. This is what we observed. And we expected, our expected value for the sum is 1/4 of, which is the average of the box, n times the average of the box, times, that's 1 out of 4 is the average of the box, times n, which is 7,500. And that is 1875. Okay? That's our observed and that's our expected. All right, so we've gone that far, and the difference between the two is that's going to be the numerator of our z-score. So now we have to compute a z-score. All right, so we're going down to the normal curve. Let's draw a curve and think about it intuitively before we even compute the z-score. And right in the center is what as a z-score? Always 0. And underneath it, we'll say what it is in this particular instance as a number of correct guesses, and it's 1875. Okay, so now our question is, this difference of 131 more, which is 2006, of this difference of 131 more, how weird is it? How unusual is it? Where should I place 2006 on here? Is this blowing you away or what? So where do you think it is? Where do you think I should put 2006 on here? 131, how weird is it? So you tell me when to stop. About 1 standard error, okay. Well, should I go, maybe other people? It goes on forever. Want me to stop? Okay, it does go on forever. All right, so there's two different, how many people want to go with this one? Raise your hand. Just pretend you don't know, just your intuition. Just your intuition, raise your hand. Don't think about it at all. Okay, how many people want to go with this one? Looks like about even. Okay, let's see who's right. So how are we going to figure this out? We're going to compute the z-score. And the z-score is what? As we've been saying, it's always the observed minus the expected, the observed value minus the expected value over some standard error. So this is our value minus the expected value. This is our observed value. This is our expected value over the standard error. It's just doing a z-score like we've been doing all along. Observed minus, it's our value that we get minus the expected value over the standard error. Now what are we dealing with? Averages, sums, percents, it's sums. We're summing it up. So this is sum and this is sum. We already know the numerator is 131. What we observed was 2006. That's how many they got correct. Minus what we'd expect, the expected value. And we already said that was 131. That part you know. The hard part is where to put 131 on here. That's the hard part. You always know the difference right away. It's just like where to put it. Okay, so the standard error for the sum. All right, that's a different formula. What is that standard error for the sum? Standard error for the sum is, we just did this last night. What is it? ST divided by the square root of n? Times the square root of n. It's ST times the square root of n. Okay, so our SD, whoa, we're stopped dead in our tracks, aren't we? Or are we? SD, they didn't give it to us. We know square root of n. That's the square root of however many guesses there were, which was 7,500. That part we know. But what's the SD of the box? That's what we have to get. How are we going to do that? Anybody? What's that standard deviation of that box? Can we figure it out? All right. It's just ones and zeros, so we can figure it out. So let's do that. So, how are we going to do that? It's 1 minus 0, the absolute value of 1 minus 0, those are the numbers on the tickets, right? 1 minus 0, but that's just going to work out to be 1, so we don't have to worry about that. We can just forget about that. Then, times the square root of what? Well, there's, why am I... My screen looks so bad. I'm glad it's not there. Okay. So what do we do? There's 4 tickets. One of them has a 1 on them, and the other have 1/4 times what? 3/4. Okay, so that's all we have to do. 0.25 times 0.75. So we do that. And we get, it's less than 0.5, I know that. What do I get? Point what? 0.4 what? 3. Oh my goodness, thank you. 0.43, that's what we get. For the standard deviation, that's what this is. Now what do we have to do with 0.43? Multiply it by the square root of what? Times the square root of what? 7,500. You want to do that for me? That's what we need. And that's what we're going to put right here. I can put this right here first, 0.43, while she's working on that, times the square root of 7,500. And this is going to give us our typical error. Going to give us right about there, or, where 68% is, this number. What did you work it out? Did you get this? Oh, yeah, there you are, behind my screen. Yeah, sure.
I'm confused. You put 1875 on the top or 7,500? Shouldn't it be 2006 minus 1875?
Yes! Oh, thank you. Good job, thanks. All right. Oh, if this was the review, you could have gotten an extra point on the review. On the exam, I should do a wake-up call now to give everybody, to keep myself on my toes. If I make another mistake, I'll have to add 1 point to everybody's exams. I haven't entered them yet, because I don't want to make any more mistakes. So I'm giving myself an incentive. So look what I did. Duh. What should be here? 1875, of course. And that's 131, thank you. All right, now, so what did this work out to be? Let's just say 37.5? 37.5. Okay, so now what is our z-score? It's going to be big. That's going to be really big. What is that? It's over 3. 3 point what? 493. We'll just say round to 3.5. Okay, so that's huge, huge. So people guessed right here, but between 3.5 and negative 3.5 on the normal curve is where? Let's just go way out on either side and go to the back of our book. 3.5, it's gonna just, it's so outrageously on 99.953. So this is 99.953. So it's just this speck here. It's just a tiny, tiny, tiny speck way out here. What I'm doing is just, so our P is equal to 100 minus 99.953 divided by 2, which is tiny. It's way less than 1%, way less. It's, what is it, like 0.0235%. That's just unbelievably unusual. So what do? We reject the null, that they're just guessing, and conclude that they have ESP, do you think? Have you concluded they have ESP? Do you think they had ESP? What are we going to conclude? Something besides chances going on. It's not necessarily ESP, it could be something else. And conclude something besides them just guessing is going on. Something besides guessing is going on. Not necessarily ESP. Put that in your notes. I don't have time to place to write it, but not necessarily ESP. It could be other things. In fact, they've never been able. So what do you think you do at this point to see if it's ESP? You repeat the experiment. And they tried to repeat the experiment many times and never got these results again. So it could be that once in a blue moon thing that happens. There is a tiny chance. This is the chance that it would happen just by guessing. So there is a 0.0235% chance that it would happen. So if they repeated this experiment over and over and over again, or they might have been cheating. Like the random number generator might not have been random. Actually, there was one experiment where they had many more than 15 people. They started off with a lot more, and the people who weren't doing well, just by the luck of the draw, dropped out. They let them leave, and the ones who had their lucky days kept on. All right, any questions on that so far? All right, so I like when you can look at court decisions, use statistics in legal and also in medical examples. And here's a really classic one where the Supreme Court used a statistical argument, just like a z-score basically. And we're gonna check their reasoning here and check their results, okay? So, in 1965, the Supreme Court decided this case of Swain versus the state of Alabama. And Swain was an African-American man who was convicted in Talladega count. So you know it? What is it? How do you say it? Talladega. Oh, good. Talladega County. Of raping a white woman. And he was sentenced to death. That was the penalty at the time. And the case was appealed to the Supreme Court on the grounds that there were no African Americans on the jury. Why can you appeal to the Supreme Court on those grounds? Because you're supposed to be judged by a jury of your peers. So even though about 26% of the adult men in Talladega County were African American. Okay. So the Supreme Court denied the appeal on the following grounds. They said that the jury was selected from a panel of about 100 randomly selected people, because that's how juries are selected, by randomly selected people, the panel. And the Supreme Court said that 8 of them were African American. So they didn't happen to serve on the 12-person jury because they were struck by preemptory challenges by the prosecution. The prosecution and the defense can both, from this panel of randomly selected jurors, can interview them and decide to not choose them. So that's how they boil it down to 12 from the 100, not in a random way. But so the argument was, so what's the argument here? They said that the presence of 8 African Americans on the panel showed, and I quoted this from their decision, quote, the overall percentage disparity, the difference between the 26% you'd expect that were in the county and the 8% that you actually got by a random selection is small, and reflects no attempt to include or exclude a specified number of Negroes, unquote. Boy, that word jumps out at me. I haven't heard that for so long. Oh. Okay, so the Supreme Court said this small difference, the very small difference, is just due to the luck of the draw. And the fellow was executed. So they said it was due to the luck of the draw, choosing 8, getting 8% when you expect 26%. So let's see if that's a small difference or not. Okay? So here we have a box, right? And we have tickets on them. And it's going to be 1 ticket for what? Everybody in the county. So I looked this up and I wrote this down, there were 16,000 male residents at the time. So we have 16,000 tickets. Not that we're going to use that number. We're not going to use this number. We're not going to use it. I'm just describing the situation. 16,000 tickets in the box. 1 for each male. Why am I only talking about men here? Because women weren't allowed to serve on juries then. Male residents in Talladega County. Okay, so that's it. And then they were all classified as either white or not white, as either black or not black. So these will be black right here, and that's 26%, and then the remaining, I guess they didn't have anybody Asian or anything else. Okay, so this is 74%. That's what they had. Okay, so now, this is white. All right, now our null hypothesis is what? That the jury panel was randomly selected, right? 100 people on the jury panel were randomly selected. Just like that's the law. And the alternative is, They're randomly selected, and this difference between the 8 and the 26 that we expected, those different, is just due to the luck of the draw. Okay, and the alternative is what? That the jury was not randomly selected. The jury panel was not randomly selected. That this difference is too huge to be due to chance. The difference between observed and expected is too huge to be due to chance. Here it's saying the difference is small, just like right here. This is the difference. That's your observed, and that's your expected. And they say the null is that this difference is small, okay, and just due to the luck of the draw. All right. Now, what do we want to do? What do we want to do here? We have to come up with a z-score. Okay, so our z-score is what? Z is equal to, it's always equal to some observed minus some expected value. Some observed value minus some expected value over some standard error. Okay? And in the numerator, we just have this difference between what we observe and what we expect. Okay? So that's going to be 8% minus 26%. So that's equal to negative 18%. Is that difference big or small? The Supreme Court said it's really small. And we don't know if it's big or small until we do what? Until we change it to a z-score. You know, as you can see, you disagree on this. It's very hard to tell whether it's big or small until you change it to a z-score. So this is 0 as a z-score, and here is 26%. And the question is, the Supreme Court said, okay, it's just small. 8% is just small. It's an 18% difference, but that could happen all the time. How do we get the SD of this box, the standard deviation? If it's 20, there's a 26% and a 74%. So it's going to be what? Just multiply this square root of 0.26 times 0.74, correct? Does everybody agree? Do y'all agree? Okay, and then times 100. All right, so let's see what we get. When we do that, we get, whoops, we have it right here. This is what we're going to, this whole thing we're going to stick right in here. And I wrote this out. This is 4.4%. Okay? So one standard error is 4.4%. One standard error takes us out to what? About a little less than 22, and then another one, a little less than 18. We're going to go, we are looking for 8% on here. Whoa, this is going to be a huge negative z-score. So that's equal to negative 4.1. That's our z-score. That's way out on the tail, way beyond a this is the most extreme we've seen so far. 4.1, if you go way, way, way out, it's so, it's off the page here, but let's just do it to here. This is between negative 4.1 and 4.1, and this is where we find our 8% to be. This is our 18% difference, minus 18%, and that speck right here The speck is the chance that it was that it was just due to the luck of the draw, that the jury panel was really randomly selected. And this huge difference, it's about as far as you can get. This is what the Supreme Court said was small. So what is this chance here? This little speck here is so small, it's just tiny. Okay? So this is our p-value, and p is tiny. It's way less than 1%. It's like, and it's equal to 0.002%. This is about, this is 99.9956% from the back of the book. So, we certainly reject the null. P is way less than 5%. It's way less than 1%. Yeah? Oh, you're looking at, don't tell me I made a mistake. Oh, everybody's on their toes waiting for the mistake. Let's see. Oh my goodness. I don't think that qualifies, but I'm curious. 99.95956, and I forgot I made that bet. Whoa. 99.9. What was it anyway? 99.956. 956. Oh, I used 4.1. Well, I went to the next line, like you do on an exam. That's okay. 5.6 to 5.9, then I went over here. Okay, so that's how I got that. Not a mistake. But thanks for trying. It's gonna keep me on my toes. Thanks. All right. Okay, so unbelievably bad. I mean, the Supreme Court was completely wrong. Are you surprised? I mean, there'd never been an African American on any jury ever. It was so much worse than that. But the statistical argument was what they used, and they were even completely wrong on that. Okay, so I think it's time to say goodbye.